Okay, in the last class we are talking about Kelvin-Helmholtz instability, and one last topic that we wanted to discuss was the problem of the mixing layer. So, we have the same fluid rho 1 and rho 2, but it is approaching the interface at two different velocity, and we worked out the characteristic exponent like this. And because there is this part with a negative imaginary part, you can immediately see that it is unstable. And the second thing that you also notice that this omega does not depend on beta. So, whatever may be happening in the y direction is not reflected in the time variation, right. So, that means the flow behavior is totally dictated upon by streamwise variation, right. And without spending too much of time, we know that when we have a collection of waves, as we have in this case, because we are integrating over all possible alphas. So, how do those alphas interact with each other? That concept is brought about by the concept of group velocity, right. So, to demonstrate this group velocity idea, let us say we have two functions f1 e cos k1x minus omega 1 t, and let us look at similarly another function which almost have the same amplitude. So, we will take it as a itself, then we will get it like this. And now, if these two waves are simultaneously present, as you can understand, this is a wave, right. The wave propagates with the phase speed c1 here, that is equal to omega 1 by k1, and for this wave c2 will be omega 2 by k2. So, this is the speed at which the phase changes. How does the energy change? That is what we are interested. So, interaction of these two waves, if I write it as f1 plus f2, then we can see that this is simply equal to 2a cosine k1 minus k2 by 2 x minus omega 1 minus omega 2 by 2 t. This part multiplied by cosine k1 plus k2 by 2 x minus omega 1 plus omega 2 by 2 t. So, this is what you get. Supposedly, say k1 and k2 are neighboring elements in the wave number space. That is, if we write k2 is incrementally different from k1, which I can write like this, and we now know what is a dispersion relation. Dispersion relation is the relationship between omega and k, like what we have shown here. This is a dispersion relation. K is replaced here by alpha. So, that is what you are seeing, that dispersion relation relates the time variation with the space variation, but not in the physical plane, but in spectral plane, right. So, if I have a dispersion relation and if I focus my attention on two neighboring wave numbers like k1 and k2, then the corresponding circular frequency would also be incrementally different, right. It would be incrementally different, and then from here what we are going to see, the f is nothing but 2a cos that will be dk times x minus d omega times t, and then what about this? This will be like an average. Okay, so that is like that variation would be like k1 or k2x. So, I could just simply write it as cos k1x minus omega 1t. So, now what you are noticing that there is a slow variation that is indicated by this part, and there is the usual variation that is your parent constituents. Okay, the parents F1 and F2 varies like this. Okay. So, what you are seeing is that two neighboring waves, when they are simultaneously present, their net effect is to cause the usual variation that each constituent has plus an amplitude now which slowly varies. And this is something what you see if you plot it for a fixed time. If I plot it versus x, then I would see that the variation would be given in a packet like this. So, the actual wave that you would see would be something like this, and so on and so forth. So, what is happening? You can see that the original waves, which are very close to each other, their amplitude actually varies between plus minus 2a, right? Right? So, the individual ones were going to vary plus minus a, but their combination varies from plus minus 2a. Okay. So, basically this is something like your slowly varying amplitude, and this idea was brought to us by actually Hamilton, and later on it was refined by Rayleigh. And what we notice is that these two signals do get modulated. This is what we call as a modulation. Two constituents getting modulated and their amplitudes traversing twice the individual constituents. And what happens? The energy is proportional to amplitude square, right? So, if the amplitude varies by this law, the energy also varies according to this law. Okay. So, what we are in essence saying, energy is proportional to amplitude square, right? So, the speed at which the amplitude propagates, that would also be the speed at which the energy propagates, right? So, basically then we conclude that the energy propagation speed would be equal to amplitude propagation speed. And what is the amplitude propagation speed? That you can see the way it is. So, what is this? This is going to be the speed at which x by t line moves. And what is that? That is what I can see, that constant phase of this amplitude would give me this, right? So, this quantity is given a name which we will call as Vg, and this is what is called as the group velocity. Right? So, what we are getting is a new concept, that if we have a collection of waves, then around the center of some wave number, we can see they all group together. And they have this constructive interference with each other, so much so that the amplitude actually doubles up in some place. Okay, those are the places where it doubles up are called the antinodes, and where it is 0 are called the nodes. And those propagate, those group of waves or wave packets propagate with group velocity. So, the group velocity is given by this d omega dk. Okay. So, this k that we talked about is basically the wave number vector. It could go in any direction. What we were studying in the context of Kelvin-Helmholtz instability, that k had two components. The x component was alpha, the y component was beta. So, I would also have a group velocity as a vector. And the individual components will be given by the corresponding relation that we are talking about. It should be written as d omega d alpha. That will be the group velocity in the x direction. And if I could get d omega d beta, that will be my group velocity in the y direction. So I just gently introduced you to the concept of group velocity to appreciate what happened in case of Kelvin-Helmholtz instability. You can very clearly see the omega is a function of alpha, but omega is not a function of beta. So what happens? If I create a disturbance, the energy will only propagate in the x direction, and not in the y direction. This is something that we need to understand and close our discussion on Kelvin-Helmholtz instability. Okay. So we have been gradually increasing the level of difficulty or the variation of the equilibrium flow. First we studied the equilibrium flow was 0 at dynamic stability of atmosphere. Now we have studied a case where we have the equilibrium flow is given by two sets of uniform flows. Now let's go over to an engineering problem, which it's really a problem not only of engineering, but it's also a problem of physics, which interestingly enough has exercised the mind of great physicists starting from Kelvin, Helmholtz, and Rayleigh. You can name anyone, any physicist who have not really dabbled with it. So now let's look at the problem where people started looking at a different idea altogether. Okay. Now the idea is what happens in a real flow, unlike what we suggested that this could be the trailing edge of an aerofoil and we could get this, but you still realize that it would not be uniform flow above and below. It will have some kind of a distribution in the normal direction, right? So basically then we can study the flow field which has this detailed variation of the velocity profile given like this. So at different height, I am going to get this kind of velocity distribution. And what is the characteristic of this velocity distribution? That this has built in a shear. So the mean flow now has a shear, whereas what we studied before is zero shear case. So that's what I said, that we are going to ratchet up the difficulty of the description of the equilibrium flow. Now we are talking about a flow which has this kind of thing. For the sake of convenience, we will always represent the mean flow with capital letter. Okay? We keep the lowercase notations for disturbance quantities. So what we have here is, of course, the mean flow. Earlier was just simply u2 was constant, u1 was constant, but here u is going to be u of y. So people who are aware of it, Rayleigh, Helmholtz, Kelvin, they were all aware of it, that the mean flow can have shear. Now the question is, when you have shear, what happens to the disturbance field? This is where actually a philosophical decision was made. This is something what we call as a paradigm. So the paradigm at that point in time, in mid 19th century, was the following, which was that look, the shear is caused due to what? Viscous action. So the viscous action that gives rise to the shear, what can it do to the disturbance field? This can attenuate. That's a very commonsensical clue that one would like to draw. That if there is some viscous action, it's going to attenuate the disturbance field. So, making that observation, all these giants of physics, what they decided to study is, instead of studying the viscous stability, they started studying the inviscid instability. So, what happens? What does this mean? Please pay attention to the flow field description. Let us say we are talking about a two-dimensional flow. So, we will have only two components of velocity, u and v, and there is the associated pressure field. We are talking about this two-dimensional field, and please also do understand, whenever you study disturbance, you study in its most general form. So, we do not presume it to be steady or unsteady, right? So, that is why we actually talk about the total velocity field and the pressure field to be a function of time, while the equilibrium flow could be time independent, but the disturbance quantities have embedded in them all possible kinds of space and time dependence, right? So, that is what we are talking about. For the ease of our analysis, please note that we have looked at a velocity profile which has only single component, right? So, that is in the streamwise direction. So, u of y, that is what we have, and this also tells us that this does not vary with x. That means this mean flow or the equilibrium flow that we are talking about is only a function of the wall normal coordinate, but it does not vary as we go along. So, what happens? What kind of flow is that? That sort of flow is called a parallel flow. Why? Because everywhere it is same. So, if I try to think up of a streamline, what will it be? For the same height, at two different stations, it will be the same value, because it is only a function of y. So, what happens? The streamlines happens to be parallel. That is why it is called a parallel flow. So, what are we sacrificing in making that assumption? We are sacrificing the growth of the viscous action. What is the viscous action? The existence of a boundary layer, let us say. So, in this framework, when we are saying there is only u of y and b is absent, we are talking about streamlines which are parallel to the wall. We are calling them parallel flows, and we are neglecting the growth of the associated shear layer. Okay. So, with that, we will begin our discussion. You now understand what is a parallel flow approximation. It is an approximation. Okay. For a flat plate, if you are looking at if this is a flat plate with a sharp leading edge, then what we are going to find that the boundary layer would form, which will have a configuration like this. If we are looking at a configuration like this, what we are saying in making that parallel flow approximation, that picture is not consistent with this part, where actually boundary layer is growing from 0 to some substantial value, and then subsequently it could remain virtually constant. And that is precisely what you actually do get to see. Even if you go to a tunnel and do the experiment, you are going to get a similar profile. So, if I leave out this part of the flow, we exclude in this study, and this is where we are kind of justified in talking about parallel flow. Right? Then of course, we also start with the paradigm of inviscid studies. Let us see what happens. Okay? So, this is the way that we are going to talk about, and I specifically made a note here that the space-time dependence of the perturbation field has not been restricted, while the mean flow has been restricted here. Okay, so what do? We try to write down the governing equations. What have we done? We have taken the Navier-Stokes equation there, and then we use that splitting that we have shown. What was the splitting? A mean part plus a small perturbation part. That small perturbation was given in terms of that epsilon. Epsilon parameterizes the smallness of the disturbance field. So let's go ahead and see what do we get. So our full Navier-Stokes equation, for example, is given by this. Del u del x, we are talking about incompressible flow, and in a Cartesian frame, that's your equation. All right. Now, what is our u? U is nothing but the mean flow plus the perturbation field. What about v? That does not have a mean component. We are talking about parallel flow. So, a parallel flow cannot have a mean v component, right? So, that's not there. Then we have this. And you can see the usual formal way of doing perturbation series is you write down the order 1 quantities and order epsilon quantities. What is order 1 quantity? It is only here. And this is nothing but your restatement of what you have actually assumed, approximated, that u is not a function of x. It is a function of y alone. So there is no contradiction here. Basically reaffirmation of what we have started with, and that's what we get. What about the order epsilon quantity? That one comes from here, one comes from there. I have just factored out the epsilon. It's multiplying each one of the terms. And that's what you see in the slide there, that mass conservation equation gives you this. So, the perturbation quantities satisfies the mass conservation in this form. That's what we have derived here. You can similarly go ahead and look at, let's say, the x momentum equation. That is this: del u del t plus u del u del x plus v del u del y. Then we will have minus 1 over rho del p del x. And since we are studying the inviscid stability, so what we are going to do, we are going to write this equation, all right. Now, you have seen, what about u? U is this plus that. And what about its time variation? We are looking at the stability of the stability, sort of a steady flow. If we are doing that, so we will not get anything there. What we are going to get? We are going to get epsilon del u prime del t. Right? What are we going to get from here? We are going to get a mean term which will be u del x. That's not there, right? Del u del x is 0, we have already seen. So, this term does not survive. What about the other term? We also get u del u prime del x. And we will not have the other term u prime into del u del x, because we know del u del x is 0. So, we do not need to really write this term out. So, this is not there. So, we do not have that. So, that is that. What about this term? What do we get from here? We are writing out order 1 term does not exist, order epsilon term will be epsilon v prime. Epsilon v prime. What about this? We will get only the mean flow term coming, that is our order epsilon term. So, that is your del u prime, sorry, del u del y, that exists, right. In fact, what you need to do, since you have assumed u to be a function of x only, you do not even need to write this as a partial derivative. You just simply write it as the ordinary derivative. What about additional term? There is additional term epsilon square, that is v prime del u prime del y, right. So, that we have written it up to whatever is there. On the right hand side, density remains invariant, so we have no problem. What about the pressure? I have a pressure term which I may write del p del x plus epsilon del p prime del x. What about terms coming from here? Nu, the x derivative, what will I get? For the mean flow, it is not a function of x, so there I will not get anything, but I will get this kind of term, right, and that is multiplied by a epsilon. Okay. What about the y derivative terms? The capital U is a function of y, so we are going to get this plus epsilon del square u prime del y square. So, we have written down everything. Now, see what we are doing. We are of course looking at order 1 quantity, right. So, what happens? The order 1 quantities are here and here, right. So, what does it tell you? This is like your channel flow equation. You need a pressure gradient to overcome the viscous resistance, right, the pipe flow, channel flow. You have to spend some energy to make the flow be there, and that is what these two terms balance each other. So, if we are writing now the order epsilon quantity, I would not keep these two terms, right. Now, of course, if we are writing order epsilon quantity, we do not need to even write the order epsilon square term. That is also not consistent. So, what we have is this set of terms. Now, of course, everywhere epsilon is there, so we do not need to write those epsilons. We could just simply get rid of them, and we will have this equation. Now, this is where the paradigm that we talked about comes about, right. What is the paradigm? That the viscous action, if it is there, it is going to attenuate, and it makes the problem somewhat little more difficult to handle. So, you understand this is the way actually the early part of fluid mechanics developed. You have the key, you look for the lock, right. So, people went about the other way. They will first get some solution and then see where it can be used. So, of course, this is a similar approach here, because we cannot handle the full thing, and then as an afterthought we say viscous action is there, it has to attenuate. So, let us try to find out the more critical case by dropping the viscous term altogether. That is the essence of inviscid instability. So, inviscid instability would mean that we do not need to look at this term, and that is what you are seeing here. 2.5. This is the same equation, we have derived it now, right. I will not derive the y momentum equation, you can do it yourself and convince that this is the equation that you want to do, right. So, basically we have now a situation where we have obtained the governing equation for the disturbance quantities, right, governing equation for the disturbance quantities. So, now what we are going to do is the same thing that we did in studying Kelvin-Helmholtz instability. We want to look for more accuracy and a little more tangible means of analyzing it. So, we represent this disturbance quantities in terms of its Fourier Laplace transform. So, for example, u prime, I will write it as a Fourier Laplace amplitude that we have indicated by u bar, and then the phase part e to the power I alpha x minus omega t, and they have to be integrated over all possible alpha and omega. So, it is basically a double integral, right. So, please do understand that we are talking about the most general space time variation, and you understand also that this course is somewhat special in the sense when we do such integral, Fourier Laplace integral, that is somewhat different than what you may have done in your maths course. There you will always take alpha as real, omega as real. Why? Because you are not bothering about growth or decay of those quantities. That is what it means, right. We have seen yesterday also when we are looking at time variation, the fact that omega can have the imaginary part indicates whether it will grow or decay with time. So, if I put the imaginary part equal to 0, I am basically studying the stable configuration. The very fact that we in this course will be talking about alpha and omega as complex implies that we are not excluding any possibility. Got to understand, remember in the initial lectures we talked about what happened to Stokes. He obtained some solutions in the physical plane, and then when he compared them with the experiment, he did not see any match. And then we quoted that Landau and Lipschitz oft-quoted remark that in nature you get those solutions which not only exist and are unique, but also those are the ones which are there despite the presence of disturbing influence. So, observable quantities are those which are also stable. So, that is precisely what you do in your mainstream courses in maths and physics, where you restrain this alpha and omega to be real, but here we would make them have complex values, and it would be one of our cherished goal to find this combination of complex alphas and omegas. We will see that most of the time it will not be feasible. So, basically on the left hand side what we have, the variables, the dependent variables are functions of x, y and t. So, here in the Fourier integral we have used x and t here. So, this amplitude must be a function of y, that is the only way it can be, right. You could ask me that why not have a Fourier series also in y. Okay. The answer to this question is not very straightforward and obvious. We have sort of inhomogeneity in the y direction. There is a bounding wall, that is why the shear has formed, right, that velocity profile has come about. So, our y is not unlimited, it is limited to an extent, so is our time also. You know, when we talk about time, we must have some origin, right. So, if I perform time integral, we are talking about that receptivity framework, right. So, if I start a wind tunnel or a water tunnel, then of course at the time of starting, I am not only starting the mean flow, I am also starting some kind of a disturbance field. And I can study that evolution of that disturbance field. So, there is a time origin, time only goes in the positive direction. Look, the moment I switch on the tunnel, the way the disturbance evolves does not depend on the past, right? This may seem a little difficult to understand, but you would understand it better if you conceive of a situation where you have very clean flow, disturbances are not affecting it, and now you introduce a source of disturbance in a very deterministic manner yourself. And when you switch on this disturbance source, that is your time origin. And the events that happen subsequently does not depend on what happened beforehand, right? So, that is what is called the causality. However, in this case, we would not use a Fourier transform in the y direction because of inhomogeneity of the flow geometry. So, we will keep it like this, and then we will see. What will we see? If I introduce two transforms in x and t direction, and the flow is two dimensional, and if I have a partial differential equation, I would end up with ordinary differential equation in y, right? That is what we would be doing. So, let us put this description for the disturbance field in terms of their Fourier Laplace amplitude u bar, v bar and p bar. So, once we have done that, what we need to do is then plug this information into our governing equation. Now, this requires a little bit of explanation. So, let me just do it gently so that you understand once for all how this process is carried out. So, let us get back to this discussion on this parallel flow approximation and inviscid instability analysis of a two-dimensional flow. And we did obtain the governing equation. Let me go back in the slide, and you can see how it was. So, we will keep that here. So, those are those three equations that we have. Now, what we have written down is basically u prime as the double integral u bar e to the power I alpha x minus omega t times d alpha d omega. Okay. So, we have similarly b prime is b bar e to the power I alpha x minus omega t d alpha d omega. P bar, sorry, p prime should be equal to its amplitude p bar times the phase. Well, although I am calling it a phase, that is a very loose way of saying, because if it has an imaginary path, it would also contribute to the attenuation or growth of the amplitude. The amplitudes are given like this, but their amplification in space and time would come about from the imaginary part of alpha and omega here. So, we should keep that in mind. So, there it is. What we have are this three definitions in the spectral plane. Let us plug it in one by one. What do I get if I take del u prime del x? I will get I alpha u bar times this phase relationship. So, I am not going to write down the phase relationship, but you can understand it is very much there. So, I have from del u prime del x should be equal to this. What about del v prime del y? That y variation is embedded in there, right? So what I would do is I will write that as dv bar dy. And then we have all these quantities that we have, alpha x minus omega t, d alpha d omega, this is equal to 0. The logic follows similarly, that if that integral is 0 for an arbitrary space-time variation, then to hold to this relation to hold, we must have this quantity must be equal to 0 identically for all possible alpha and omega, right? So basically, this equation then comes out to this. Sorry. So you see, that's what I promised to you, that the PD will be converted into OD. Can you not see that? That what we have is a differential equation where the derivatives are with respect to y alone. What about the 2.5? If I do it, what do I get? From now on, I'll just simply be worrying about the kernel of the integral, right? Like this. So del u prime del t will give me what? Minus I omega u bar. So I will have minus I omega u bar. That is the first term, del u prime del t. What about the following term? U is a function of y only. So when I write down the Fourier transform with respect to x and t, it's like virtually like a constant, right? So there I will have the capital U sitting there as it is. What about del u prime del x? Del u prime del x again is going to be I alpha u bar, right? So I'll have I alpha u bar. Okay. What about v prime du dy? That is much simpler. That will be simply v bar du dy. Right? And on the right hand side, what we will have? Minus 1 upon rho, and del p prime del x will be I alpha p bar. Right? So that will be that. Okay. And so this is let's say equation A, this is equation B coming from x momentum equation, and what is the last one? Last one will come from here, 2.6. Del v prime del t will give us simply minus I omega v bar, and u plus u times del v prime del x will give us I alpha u v bar, right? And on the right hand side, I will have 1 upon rho. And what about del p prime del y? That will be simply dp prime dy. Right? So I have basically three equations for these three Fourier Laplace amplitudes, u bar, v bar, and p bar. Okay. Now I could use this equation A, and I can see that u bar is nothing but minus of 1 over I alpha dv bar dy, right? So I could actually put these two together, and what I would get, I have two terms there, which I can write. If I write I alpha, then what do I get? u minus omega by alpha into u bar. See, there is this u bar. And from here, u bar, I have found out what it is. So, I will write that u bar is minus 1 upon I alpha times dv bar dy. That is that term. Then of course, I have the v bar term. So, that is v bar du dy, and that is equal to minus I alpha by rho v bar. Okay. So, what we have done in a sense, eliminated u bar, right? We have eliminated u bar from A and B. Now, between these two equations, we can eliminate p bar also. What do? I differentiate this last equation with respect to y, and then I have an expression for dp bar dy in terms of v bar. So, we can do that. We can do that. What would we get? So, here as you can see, this I alpha goes off. So, what do I get? Minus u minus omega by alpha, and we are differentiating it with respect to y. So, I will get d2 v bar dy square, but please note u is also a function of y, right. So, I will also get another term which will be du dy into dv bar dy. That we will get. What about here? From this, I will get dv bar dy times du dy, and then I have another term v bar d2u dy square. That will be equal to minus I alpha by rho dp bar dy. So, of course, you can see these two terms cancel out, right. This two term cancels out, and then you get this. You get this expression minus of u. What is omega by alpha? Omega by alpha is the phase speed. That's the definition of phase speed. So, I will write it as u minus c. Okay, and then I have d2v bar dy square plus v bar d2u dy square is equal to, I will have to get this. So, I have 1 upon rho is there. So, I will get minus I alpha, and within bracket I will have that expression minus I omega v bar plus I alpha u v bar. So, this is a simplified form. So, we have eliminated basically u bar and p bar, and this is what we get. That is the equation, simplified. Simplified, that is what you get. So, there we have retained omega by alpha as it is, but that is what you are going to get. Right. So, you can see here also I can on the right hand side I could borrow that I out, and I square will give me minus 1. So, I will get minus alpha, okay, within parenthesis. If I make it alpha square, then here I will get minus omega by alpha, and here I will get plus u, and that will be multiplied by v bar. All right? So that's what it is. So essentially we are getting u minus c. So that's what you have. So you can put this inside, and then you will find the quantity u minus c will be multiplied by the second derivative of v bar with respect to y minus alpha square v bar. That's what you are seeing here. So that's the derivation of the equation. So once you have that, it's very easy for you to look at it. Now, I said some time ago that in stability studies, you want to keep the condition as general as possible, and you try to have alpha and omega both complex. That turns out to be quite difficult thing to do. So we have to adopt a point of view. What we could do is we could talk about a temporal instability where omega will be complex and alpha will be real, and we will talk about a spatial instability where omega will be real, alpha will be complex. So we'll start off from this in the next class. Okay? So we'll adopt for this problem a temporal instability approach. Okay? I'll stop.